In this lecture, we begin to see the weighted version of the single source shortest path problem. Our input here is a graph which is possibly directed. We have a source node S, and we have a weight function W which assigns integer weights to the edges. For example, here I have assigned weight 7 to the edge A to B and weight 15 to the edge B to C. And the output again is the shortest path from S to all the other vertices. And naturally I want the shortest with respect to the weights. In the previous case, in which I did not have weights, it's like our weight function simply mapped every edge to 1. It's important to note that if the weights can be negative, then a shortest path exists if and only if S cannot reach a cycle with negative weight. Okay? So a cycle at negative weight is if you sum all the edge weights along the cycle, you get a negative value. If S can reach something like this, then you can get to an arbitrarily low weight simply by going around the cycle over and over again. So we begin with the algorithm known by Bellman and Ford. Okay? It is quite simple to describe. So its input is a graph G, a weight function W, and a source node S. At the beginning, we set the distance of S to 0 and all the others to infinity in our array D. And then the algorithm simply repeats a simple operation for number of stages, which is the number of nodes. Okay, so for number of node stages, we simply go through every edge in the graph in any order that you want, and you relax the edge. Relax the edge means the following. If the edge is UV, you set the distance of V to the minimum of its current value and the distance of U plus the weight of the edge UV. Okay, this operation is called a relaxation of the edge UV. So you simply repeat this. So V times you relax all the edges, and then you're done. As a bonus, at the end of the algorithm, you can also detect the presence of negative cycles as follows. You can go through all the edges in the graph. If for any edge UV you have that the distance of V is strictly bigger than the distance of U plus the weight of the edge UV, then you claim that there is a negative negative weight cycle. Otherwise, if this never happens, then you're going to return that no negative cycle exists in the graph. So the Bellman-Ford algorithm accomplishes two things. First, it computes the minimum distance and also allows you to know if there are negative weight cycles in the graph. Let's see an example of the algorithm. So here is a graph. The nodes are labeled S, T, X, Y, Z. There are the distances inside, 0, infinity, 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 and there are weights. So this edge here has weight 6. And we also have negative weights, like -2 here, -4 here, and so on. Okay, so the first thing that we do, we relax all the edges. So for example, the edge ST here, right? Distance of t is infinity, so now I'm going to set it to 0 plus the weight of this edge here, so it becomes 6. Okay, so I have a 6 and a 7 after relaxing these two edges. Okay, the next thing that happens is that these two infinities also get relaxed. So this value here becomes 4 because it's 7 plus minus 3. Okay, and this value here becomes 2 because it's 6 plus minus 4. Okay, a different way to relax this thing is going here. That would have been a 7 plus 9, but you go through every edge and you keep taking the minimum. So if you do this before that, then the second value will be overridden. The second value will remain. If you start with this and then you do this, the second relaxation will not have an effect. Okay, and we are not quite done. We have to repeat this v times. We just done it twice, and in fact at the next iteration something changes. This distance 6, okay, will now become 4, okay, because if I relax the edge xt, then the distance of t can be as small as 4 plus minus 2. So sorry, this becomes 2. And then again, if we relax one more time, we're going to relax the edge tz among others. So the distance of the node z will become 2 plus minus 4, which is minus 2. So some nodes can also have negative distance. And now that's it, we are done. Okay, so this is the Bellman-Ford algorithm. What is the running time? Well, it's a straightforward analysis. Okay, we repeat v times relaxing all the edges. Relaxation takes constant time, so the time is order of VE. Okay, and now we're going to spend a little bit of time on the analysis of the Bellman-Ford algorithm. So here is the entire algorithm. Okay. And the claim that we want to make is that if you have no negative weight cycle in the graph, then at the end of the algorithm, d is going to be equal to delta. What you compute d will be the true shortest distance in the graph, delta. Okay, and here is a proof. So from the source node, let's take a shortest path to some other node u sub k. Okay, because you don't have negative weight cycles, this path has to have length at most n. Okay, and the claim is that at stage I, when I goes from 1 to b, you will have that the first I nodes in this path after S will have the right value for D. So D of U sub I will equal to delta S of UI. And this can be proved by induction. Okay, so at the beginning you definitely have the right distance for S. Okay, and in the future, if you have the right distance for some node U sub I, okay, and when you relax the node, when you relax the edge UI goes to UI plus 1, then the distance of UI plus 1 will be said to be the delta of S UI plus 1, okay? Because this thing is the shortest path, the way to get to UI plus 1 is indeed to go to UI and then follow this edge here. Okay, so d of ui plus 1 will be equal to delta. And throughout the algorithm, the value d is never increased. Okay, so you will never go above delta, and also it's never set below delta. Okay, so once you do this thing once, this value will stay like this forever. It is clear that d is never increased, and it can also be verified that you will never set it to below delta. Okay? It is in fact a general fact that if you have an algorithm that starts with d of s0 and infinity otherwise and only does edge relaxations, then you will always have that d is at least delta. Okay? You will never set d below the true distance in the graph. The only other thing that requires some thought is the analysis of the negative weight cycle detection at the end of the algorithm. Remember that after we do all of our edge relaxations, we can check if there is a negative weight cycle in this way. We simply go through every edge in the graph, and if the edge is uv, we check if the distance of v is strictly bigger than the distance of u plus the weight of uv. If that's the case, we claim that there is a negative cycle, and if not, we claim that there is no negative cycle. Let us see the proof of correctness of this. Why is this a valid thing to do? These proofs are useful because they build our intuition of graph algorithms. Okay, so first let us observe that if there is no negative weight cycle, then we claimed before that d will be equal to delta. And when d is equal to delta, then all these tests will pass. Okay, the true distance delta never satisfies this. Okay, the distance of v is always at most the distance of u plus the weight of the edge ub. This is known as the triangle inequality. Okay, otherwise, suppose you do have a negative weight cycle. So you have a cycle like this: u1 goes to u2, goes to something else until it goes to uk, which is equal to u1, and assume that the sum of the weights in the cycle is less than 0. Okay, so the sum for I less than k of the weight of ui to ui plus 1 is less than 0. Okay, suppose now that the algorithm didn't detect the cycle. This means that this thing never occurred. Okay, so it was the case that d of ui plus 1 is always at most d of ui plus the weight of ui plus the weight of the edge ui to ui plus 1. Okay, because otherwise we would have detected it. Now the idea is that we know this condition about the weights. We know this for all the nodes, so we're just going to sum this over all nodes. Okay, so what we do now, we simply take the sum of this, and sum of this. So if you sum this, you have this, the sum of this. You have the sum of this, and then you have the sum of the weights. So the cool thing now is that we know that this sum here is the same as this sum here. Why is that? This follows just because this thing here is a cycle. Okay? And then this sum here of the weights, well, by assumption, it's a negative weight cycle, so it's going to be less than 0. So what we got here is that something is less than itself plus something negative. That's the same thing as saying that 0 is strictly less than 0. This doesn't make sense, which means that the algorithm will actually detect the negative weight cycle at some point. And this concludes our exposition of the Bellman-Ford algorithm. It's a very cool and simple algorithm for the weighted shortest distance in the graph, which also allows you to detect the presence of negative weight cycles.